Okay, so in this lesson, what we're going to look at is this idea of the modulus of a complex number. So again, we looked at this in the last lesson, so this is called an Arn diagram. Now, what we can do with this is we can plot an imaginary number on this diagram. So remember, we have this horizontal axis, represents the real part of the complex number, and then we have this vertical axis, which represents the imaginary part of the complex number. Now if we take, for example, this number here, so remember z1, so this z1 is just a placeholder, is equal to, and this is the complex number, 2 plus 3i. So you have, and let's make this minus 2 plus 3i, okay? So you have the minus 2 part, which is the real part of the complex number, and then you have the plus 3i, which is the imaginary part of the complex number. Now what I can do is, I can plot this complex number on this diagram. So the first thing I want to do is, so along the horizontal axis, I'm minus 2. So if I look here, so this is minus 1, this is minus 2. So I'm here, so let's say I'm here. And then if I take the imaginary part is plus 3, which is here. So I have 1i, 2i, 3i, so it's up here. So if I want to plot minus 2 plus 3i, I'm going to go minus 2, and then I'm going to go up here to plus 2 plus 3i. So this here is where I'm going to plot this number. Now, if I want to get what's called the modulus of a complex number, basically what I'm trying to do is, so if we imagine, so imagine here in this the middle of the Arn diagram, so this here is going to be 0. Okay, so 0. Now another word for this middle part here, or where it's 0, it's called the origin. So the origin is this middle part here. So this is the origin. Now what I'm trying to do when I want to get the modulus of a complex number, I'm trying to find the distance from the origin to this complex number here. So for example, if I was to draw a line, let's say from the origin up to the complex number, so let's see if we can draw this. So imagine I was to draw this line here, and I was to measure the distance from here to here, then what I'm doing is I'm getting the modulus of the complex number. That's what I'm trying to get. What we'll notice is that if we have a look at this, if we draw, let's say if I draw a line down from here to here, so I draw a line down from here to here, and then if I just make this bold here, what I'm going to notice is that I actually have a right angle triangle here. So for example, this here is a right angle triangle. So imagine, so let's say I can call, let's say down from minus 2 to 0, I could call this A, for example, and then from 0 to minus 3, which would be this dimension here, I can call this B. Okay, then what I can say is that the distance from here to here is going to be the square root of A squared plus B squared. And we can use this guy here to figure out the modulus, for example, or the distance from the origin to the complex number. We can work that out, and that's the formula that we use here. So for example, so the complex number in this case is z1 is equal to minus 2 plus 3i. So we have the real part and the imaginary part, and then this is the formula that we use to figure out the modulus. So the modulus, so z, okay, is equal to, and then all this is just representing is the complex number. So the modulus is equal to the square root of a squared plus b squared. And to try and kind of understand this, we need to go back to Pythagoras Theorem. So if we have a look at this, so what we have here is Pythagoras Theorem. So if you have a right angle triangle, so the length of this side here, the length of this side, c squared is going to be equal to a squared plus b squared. That's how we work out the length of this. So imagine if we, let's say if we just work with a figure here. So imagine b is equal to, let's say b is equal to 2 and a is equal to 4. And we want to find out what is c. So what we can do is we can use Pythagoras Theorem. So we know that c squared, okay, or the distance from here to here, is going to be equal to, in this case, it's going to be equal to a squared, which is 4 squared, plus b squared, which is 2 squared. Okay. Now let's say if I want to figure out then, so I want to get c on its own. So remember, this is a power. So in order to get rid of the power, I have to get the square root of it. So I have to get, in order to get rid of this, so I'm going to have to get the square root. So it's going to be, so I'd have to, so let's say I have to get the square root of this, and I have to get the square root of this. So if I get the square root of this side, I have to get the square root of this side. And what this will do is this will cancel out this power, and then we're just going to be left with c. And c then is going to be equal to, c is equal to the square root of 4 squared plus 2 squared. Okay, so that's what c is equal to. And then what I can do is I can work this out. So this is equal to, so 4 by 4, 4 and 4 is 8, 8 and it's 16. So it's going to be the square root of 16 plus 2 by 2 is 4, okay, which is going to be equal to the square root of 20. And then we can work out, it's not going to work out even, but c is going to be equal to the square root of 20. So again, so we're using Pythagoras' theorem to get this length. And this is exactly what we're doing here with this, except the a part is going to be the real part, the units, the real part of your imaginary number, or your complex number, should I say. And then the b part, okay, this height here, is going to be the imaginary part of your number here, like so. Okay, so let's have a look at that and let's see how this works out with this particular example here. Now what's important to note here as well is that when we're, so for example, when we're getting the square root of a squared plus b squared, remember b squared is the coefficient or the number that's in front of the I. You don't need to include the I, you just include the number that's in front of it. So in this example, the number that's in front of I, or the coefficient, is 3. Okay, so that's all that your b squared. So you're only putting in the coefficient of the imaginary number. So let's have a look and see what does that look like for this particular example. So again, what we're trying to do is we're trying to get the modulus of this complex number. We've plotted this complex number on the Arlen diagram. So this here is the complex number here. So this is the point. So we can say that this point up here is 2 plus 3i. 2 plus 3i. Okay, so the 2, so sorry, minus 2 should I say, minus 2 plus 3i. So this is the minus 2 part, so we're going from 0 to minus 2. This axis represents the real part of the number, and then we're going from 0 up to plus 3, okay, and then this part b is represented by the complex number, the imaginary part, plus 3i. So then we want to use this formula here. So the modulus of z, which in this case z, where z is this complex number, a plus bi, so this is the a part, this is the b part, is equal to the square root of a squared. So remember, if we have a look at this, so this is going to be the a part, and then this is going to be the bi part. So what we're trying to do is we're trying to get, so if you like, z, the modulus of z1 is going to be equal to a squared, so it's going to be equal to the square root of a squared, which is minus 2 to be squared, plus b squared, which in this case is going to be 3 to be squared, like so. So then we can work this out. So this is going to be equal to the square root of minus 2 multiplied by minus 2 will just give me 4. And then 3 by 3 gives me 9, so it's plus. So 4 plus 9. And then if we add these together, so it's going to be equal to the square root of 4 plus 9, which is 13. So therefore the modulus of this number, of this complex number z1, is equal to the square root of 13. So the distance from, let's say, the origin to where the complex number is plotted, so this distance here, is equal to the square root of 13. Is equal to the square root of 13. And that's it. Like, it's pretty straightforward, like when you're working out the modulus. So the first thing you need to do is just plot your complex number on the diagram. Then you need to plug in the imaginary part, sorry, the real part and the imaginary part into this formula, and then you work the formula down to whatever works out. Sometimes, like, it'll be like you'll be able to get the square root of the number. Other times you can just leave it as the square root. For example, in this case, the square root of 13. So that is the modulus of a complex number and how you work out the modulus of a complex number and what it actually is. Okay, so hopefully that makes sense. Maybe I'll just do one more just before I leave it so that we can work out, so we understand what we're doing. So if I take the complex number, so imagine this is my complex number. So my complex number is 3 plus 4i. So 3 plus 4i. And I want to get the modulus of this number. So the first thing I want to do is I want to plot this on my diagram. So again, the real part, the real part is 3, so this is 3, and then I'm going up to 4i, so I'm going up to here. Okay, so this is 3 plus 4i. And what I'm trying to do is I'm trying to get the modulus. So the modulus is the distance from the origin right the way up to here. Okay, so this distance here. So that's what I'm trying to find out. What is that? What is this distance? So remember, this forms a right angle triangle. So if we have a look at this, so it forms a right angle triangle. So if I drop down this part here, and then I can bold in this part here. So what I have there is a right angle triangle. So this here is a right angle triangle. So we can call this bottom part A, we can call part this B, and then the distance from here to here is going to be the square root of A squared plus B squared. Okay, just like what we've done here with Pythagoras Theorem when we're working it out. So what I've been asked to do is I want to get the modulus of this number here. So in order to get the modulus, I use this formula here. So this here just represents the modulus. So for example, the modulus of this number, so imagine this, we call this complex number Z2. So Z2 is equal to this. So again, the complex number is going to be Z2 is equal to A plus B I, which is equal to the square root of A squared plus B squared. And if we look at the complex number, so this is the A part, and then this is the B part, this number here. So what we can do then is we can just plug these in, we can just plug in the values that we have here into our formula. So what does that equal to? So what we can say then is that Z2 is going to be equal to the square root of A squared, which is going to be 3 to be squared, plus B squared, which is 4 to be squared. And you can put these inside brackets, or you can leave them, you can just write them like this as well, it doesn't matter either way. So we work this out, so what's this equal to? So the square root of 3, so 3 by 3 is 9, plus the square root of 4 is 16. Okay, so we're just working this out, and this is equal to the square root of 9 plus 16 is 25. Okay, and then the square root of 25 is equal to 5. Is equal to 5. So what we can say is that the modulus of this number here, this complex number 3 plus 4i, is equal to 5. And what we mean if we look on our diagram, what is the modulus? So the modulus is the distance from the origin, which is here in the middle, to the complex number. So it's this red line here, that's called the modulus. And in this case, we worked out that the modulus is equal to 5. So the distance from here to here is equal to 5. And that's the modulus. Okay? And when we worked out this one, it was a square root of 13. It just wouldn't, like, we can't work it out, as in, it's just we leave it as the square root of 13. But in this one, it does work out, and it works out as 5. So the modulus is 5. So again, we can do that. We can do this for any complex number. We can plot it on our diagram, and then we can work through the steps and use this formula to work out what the modulus is. Okay, so we will leave it at that, and thank you for listening.